Why is it?
Actually, I met him first time last year at a conference in ICPS. Really performed.
It is good fun.
Initially, first one or two talks, because he's like really running around near the speaker, and then you get used to it. Yeah, it's fun to have.
Yeah, it's fun to have, yeah. No, he and Puneet also is good fun. You know, Puneet? Yeah, he's last.
I couldn't recognize him.
Yeah, he has put on a lot of weight. So I met him first time in 2000 in Toulouse, actually.
Yes,
So he used to be in Mexico those days, and he was visiting Toulouse. And
Start with the mic.
So good morning. So let's start today's session. The first speaker is Satya, and 35 plus 5.
Okay. Okay, so good morning, everybody, and I would like to start by thanking the organizers, Arnob and Pinaki, for the invitation. And it's a great pleasure to be back to IMSC after many years. So I'm going to talk about correlated resetting gas, and I'll explain to you what I mean by that as I go along. And this is a sort of recent series of work which was done in collaboration with Marco Biroli, who is my graduate student. He's the next generation of Birolis. And then Manas Kulkarni, Hernan Laralde, Sanjeev Sabapandit, and Gregory Sher. And these are sort of published in some recent references. The last one is about quantum gas, which I won't have time to talk about today, but I'll mostly focus on classical resetting gas, and I explain to you what I mean by that. All right, so here's the sort of outline of my talk. So I'll first take some time to explain to you a little bit, remind you a little bit about a correlated gas, strongly correlated gas in thermal equilibrium in one dimension, for example, and what are the main observables that one is interested in. And this is a very age-old subject, but it has seen a revival due to recent cold atom experiments and so on. And then I will talk about again, a strongly correlated gas, but now in a non-equilibrium stationary state, and which will be created by stochastic resetting that you heard about yesterday in Supriya's talk and Sir John's talk. And then I'll talk about some physical observables. Some of them are macroscopic, like average density of the gas, and then, you know, the extreme statistics or the spacing distribution between particles, and then full counting statistics I'll explain to you as I go along. And finally, I'll summarize and conclude. Okay, so that's the plan. So let's start with just a very simple system of one-dimensional correlated gas in thermal equilibrium. What do I mean by that? So imagine that you have, I mean, you can define it in any dimension, but for simplicity, I'll just focus in one dimension. So you have a bunch of particles on a line, and they are subjected to a confining potential V of x, which could be harmonic or anything. And so this configuration is specified by the positions of the particles. And so these particles are in general interacting. So the energy of the gas for a given configuration, you can specify the energy. So there is the external potential term, which is this V of xi. And then, of course, you have interaction. You can have a two-body interaction. You can have three-body interaction. Very generally, you can have any sorts of interactions. They could be short-range or long-ranged, whatever. So this is the very general setting of a correlated gas. And so in thermal equilibrium, as all of us know, that the joint distribution of the position of the particles, which means that the probability of a given configuration, is given by the Gibbs-Boltzmann weight, which is e to the power minus beta, which is the inverse temperature times the energy of the configuration. And there's a normalizing constant, which is the partition function. So this is the textbook stuff. Okay. Now, of course, I mean, here we know the equilibrium measure exactly, but even knowing that, to calculate several experimentally measurable observables are not that easy. And as I said, this is an age-old problem, you can find in any textbooks, but typically, I mean, in textbooks, I mean, you have a sort of interacting gas, but they are considered, usually it's considered as a homogeneous system, like in a big box or something. But in the cold atom context, where this is an optical trap generated, in the lab, and where the particles are confined, so there the system becomes inhomogeneous. So it's not translational invariant anymore. And as a result, many things can change, as we'll see, in a short while. And so one would like to understand, for example, that given this probability measure, what can we say about the different observables? And the main point here is that in presence of interactions, okay, so this joint distribution does not factorize into individual marginal distributions. It will happen if the red terms are all zero, that means a non-interacting ideal gas. So in that case, there will be perfect factorization. But if they are correlated, you cannot, and this is the main source of technical problems of calculating any observables. So what kind of observables you are talking about? So there are many observables. It could be, as I said, this is an inhomogeneous system. So the first thing you can ask is what is the average density? So in an ideal gas in a box, of course, the density is uniform, constant. But here, because of the trap, confining trap, the density itself, which is just the fraction of particles between, average fraction of particles between x and x plus dx. And so that object itself has a non-trivial x dependence, it's inhomogeneous. So that's a macroscopic observable, which you can easily measure in the experiments. And then you can go for microscopic observables. For example, I can order the positions x1, x2, x3, xn in increasing order. So m1 is the position of the rightmost particle, m2 is the second rightmost particle, and so on. And so these are called order, and you can ask the statistics of them. So for example, you can ask what is the distribution of the rightmost particle position, so which is the maximum of these guys, what is the position of the next rightmost particle, and so on. So that's called the order statistics. And you can ask for the spacing, that what's the typical spacing between the particles in equilibrium. And you can ask the distribution of the spacing, not just the average spacing, but you can ask the distribution of the distance between the kth particle position and the k plus 1th particle position. So this is called the kth gap, essentially. Then you can ask other observables like full counting statistics, which means that I take an interval minus L to plus L, and I just count the number of particles inside this interval, and that's a random variable fluctuating from one configuration to another configuration. You can ask what is this distribution of this number of particles inside this interval. Okay? So these are the standard observables that people try to compute or measure in the experiments and so on. So these are the sort of main observables of interest. Okay? So here the problem is very well defined. You have given me the equilibrium measure. So after that, it's a technical problem. Given this equilibrium measure, how do I calculate these objects? And that is the usual statistical mechanics, essentially. Okay? Now, of course, it's very generally hard to compute for a correlated interacting gas because you cannot factorize this distribution here. Okay? So interactions make it very difficult to compute these objects. So there's one case which is this when there is no interaction, which is the ideal gas in an external confining potential. So in that case, as I said, the joint distribution, which is just e to the power minus beta exi, and it just factorizes because there is no interacting term, and each of these p of x is just e to the power Gibbs way. Not that difficult. Okay, it's still, once you know this marginal distribution p of x, which is e to the power minus beta v of x, you can calculate all these observables very easily. For instance, if I want to look at the order statistics, that is the probability distribution of the kth maximum. So what you do is you just take one of the guys to be at, let's say I'm asking what's the probability that the kth maximum has a value w. So that means one of them has to be w, then k minus one of them has to be less than w, and n minus k of them has to be bigger than w, and they are independent, so it's a product. And there's a combinatorial factor because this guy can be any one of the n guys, essentially. Okay? So it's very easy. So it's explicit in terms of this p of x. You give me p of x, I can tell you what is the order statistics, and you can analyze this. Similarly, the gap statistics, for that, I need the joint distribution of mk and mk plus 1, the position of the kth particle and k plus 1th particle. Once I know the joint distribution, which can be again written down explicitly in terms of p of x, you can actually compute the gap distribution and so on. And similarly, the full counting statistics, which is the probability distribution of the number of particles between minus L to plus L. So this is the random variable. So clearly, these particles are independent, so therefore it just has a binomial distribution where QL is the occupation probability. That means what's the probability that one of the particles lie between minus L to plus L. Okay, so this is just a QL. So once you know QL, which you know of course because you know P of x, so you can actually compute the full counting statistics also. So basically what I'm saying is that in absence of interaction, all these observables can be explicitly computed in terms of this P of x, which you know also explicitly. Okay? But of course, when you have interaction, it becomes much more difficult problem. So there are two types of interaction. So it could have a short range interaction, which means there is a finite correlation length in the system. And so then there are still methods by which you can compute these observables, for example, using perturbation theory or denormalization group method, etc. But the problem becomes more complicated when the system is long-ranged, which means that the correlation length is bigger or comparable to a system size. So all the particles are very strongly interacting. So there, it's much harder to compute these observables. Okay, and there is no general method for that. Okay, so in a recent book that we wrote with Gregory Scher, so there's some of these examples are discussed there. So just to show you that one example of a strongly correlated gas, this is the famous Dyson's log gas in one dimension. So which means that here the particles are again confined in a harmonic potential, and you scale with the factor n in order that all the positions are of order 1. And then there's the interaction, which is the two-body interaction, pairwise interaction between all the particles. Okay, and this interaction is repulsive, and it behaves like log of xi minus xj in one dimension. Okay, so it's not really Coulomb interaction. Coulomb interaction log is only in 2 dimension, but here although they are repelling each other by 2-dimensional Coulomb interaction, the charges are confined on a 1D line. So this gas is particularly very well known because it appears very naturally in random matrix theory. So just to very briefly tell you where this gas appears. So imagine that you have a n by n matrix whose elements are independent apart from the symmetry that is a Gaussian Hermitian matrix, and each element is independently Gaussian. Hij is the element of the ijth element of the matrix, and they are independent Gaussian. So therefore you can write down the joint distribution of the entries of the matrix as a product of the individual Gaussian distributions. And if you choose the variances in appropriate way, you can write this as exponential minus n trace of h dagger h. And so the point about writing this, it means that if I make a unitary transformation of my change of basis, okay, of the if you think of this as a random Hamiltonian, then this probability distribution of the entries is independent of the basis. Okay, and this is the famous Gaussian unitary ensemble of random matrix theory. Gaussian, it's called Gaussian unitary ensemble because it's invariant under unitary rotation. So this is the joint distribution of the entries, and the whole game of random matrix theory is to ask what is the joint distribution of eigenvalues. So you give me the matrix, I can diagonalize it because it's a Hermitian random matrix. So you have all the eigenvalues are real, and you can ask what is the joint distribution of the eigenvalues. And it turns out that these joint distribution of eigenvalues, they are strongly correlated. In fact, the joint distribution was computed by Wigner long back. So it has this of this form, which is exponential minus n lambda I square, and then there's the repulsive term, which is lambda I minus lambda j square. Okay, so this is I less than j for every pair. So this is called the van der Monde term, basically. And without this term, again, it will factorize, so it will be ideal gas, basically. But because of these repulsive terms, and this is the famous eigenvalue repulsion that people use in nuclear physics, for instance, that the eigenvalues, they don't like to be next to each other because this probability vanishes when the two eigenvalues are very close to each other. Okay, and in fact, you can write down this lambda square as e to the power 2 log of lambda, and therefore you can cast it in the language of the one-dimensional correlated gas. And what you see here is that the energy of the gas is just a external harmonic potential and then logarithmic repulsion. And so lambda i's you can interpret as the positions. So eigenvalues you can interpret as the positions of a gas on a 1D line and with a pairwise log repulsion. And that's why this is the example of so if you know all these observables as spacing distribution or the right average density and so on. So those are actually computed for the log gas or random matrix theory for a very long time. The whole there are many books on this subject, and you can compute exactly, but they're not that easy to compute. Okay, so for instance, if you look at the average density, so you would expect more particles to be near the trap center. So the trap is like this. So trap center there will be more particles, and as you go away from the trap center, the particle density will decrease. And in fact, this is the large n limit, the scaled variable, the density, is given by the famous Wigner semicircular law, so which is this semicircular law. So there is more density at the center, and then it goes to 0 at the edge. And then people have calculated, for example, the distribution of the M1, which is the largest eigenvalue. So this is given by the famous Tracy-Widom distribution, which says that on an average, the largest eigenvalue is located at the edge of this density, Wigner's semicircular law. But there are fluctuations, and fluctuations of order n to the power minus 2/3, and then you can actually compute the distribution around this width fluctuation, and this is the Tracy-Widom distribution. You can also calculate the several large deviation probabilities and so on. I'll not go into the details. There's a huge literature on this subject. There are books and review articles and so on. So, but just to show you that the moment you put strong interactions between the particles, and here it's a strong because everybody is interacting with everybody else, so there is no finite correlation length in the system. Then the problem even to compute anything becomes very hard. I mean, the whole subject of random matrix theory is essentially to compute these observables, knowing the joint distribution of the eigenvalues. All right. So this is about equilibrium gas, where you know the density. Okay. So now I'm switching over to non-equilibrium gas, and what do I mean by that? Strongly correlated gas. So in a non-equilibrium situation, and I'll give you examples of that. So unlike in equilibrium systems, so essentially, the dynamics decides the stationary state, and the dynamics typically violates the time reversal symmetry, or the detail balance, if you like. So often, we don't even know what is the joint distribution of the particles in a non-equilibrium stationary state. It's not given by Gibbs measure, and it's typically very hard to compute, okay, explicitly. So that's a number one problem, that we don't even know which measure to start with, okay. In equilibrium system, at least that part is there, that is, you know which distribution to start with. But here we don't even know that. That's number one problem. And number two problem is that even if we can determine somehow this joint distribution explicitly in the stationary state, computing these observables like average density, extreme order statistics, etc., they are typically very hard due to the presence of the strong correlations. Okay, so the goal, at least for this talk, would be that to find some systems which are, interacting many-body systems, which are in a non-equilibrium stationary state, number one. They are strongly correlated, because that's the interesting part about it. And they're still exactly solvable for these observables. Okay. So can we construct a class of models, for example, simple models, where these three properties hold? Okay. And what I want to show you today is that indeed it's possible to generate a whole family of models which actually satisfy all the three properties. And this is actually done by stochastic resetting. And so what I'll do is, even though this was discussed yesterday by Supriya and John, I'll just remind you, for those of you who are not familiar with stochastic resetting, just very briefly about what is stochastic resetting, and then how we can use stochastic resetting to generate a strongly correlated gas in a non-equilibrium stationary state. Okay. So stochastic resetting is a sort of subject which is relatively young in statistical physics, about 13 years old, but it has seen quite a bit of developments, both theoretical and experimental, over the last decade or so. And there have been many problems, and there's an explosion of activities, because there are many applications of this basic idea, and there are various review articles. Arnaud was involved in one of the reviews, and and so many other people in this audience have also worked on it, as you heard yesterday. And so let me just very briefly tell you what is stochastic resetting. I mean, if you don't know anything else, it's very simple. So imagine that you have any system which could be deterministic, stochastic, classical, quantum, any system, whatever system you have, and x of t is just the the degrees of freedom. I mean, it could be just the position of a particle, or it could be just a configuration, and this is time. So it has its own natural dynamics, which again could be deterministic, stochastic, classical, quantum, whatever. So you evolve it up to a random time, tau1, and after this random time, you just reset back to its initial configuration, initial or any other configuration if you like. So you don't let it evolve indefinitely, you just stop it at random time and you go back to the initial state, and then you restart the dynamics again. Again, it goes by natural dynamics, and after some random time tau2, drawn from the same distribution p of tau, again you reset and you will let it evolve. That's it. So it obviously has a renewal structure inbuilt into it, because once you reset, it forgets about the memory of the previous, what happened before previous reset. So all you need to take care of is what happened after the last resetting. Okay? And these intervals, tau 1, tau 2, tau 3, they are statistically independent, and this is the sort of renewal process structure. And the most popular resetting protocol is you choose this from an exponential distribution, r e to the power minus r tau. This is called Poissonian resetting, where 1 over r is the typical time scale between two successive resettings. Okay? So r is like a rate of resetting. So if you do that, then what happens is that in long time limit, in many situations, the system reaches a stationary state, and we'll see that in a minute that this stationary state is actually a non-equilibrium stationary state. To see this, let me go back to the original example that just a simplest example is just a single particle diffusing and then resetting. So this is the example which was discussed by Supriya yesterday. And so just think of just in one dimension as a simple model. You have a single particle which is diffusing, and then after some random time with rate r, you reset, and then it goes on like this. Okay, so essentially, if you are doing Monte Carlo simulation, you would write down your update dynamics, if you like, position of the particle at time t plus delta t in continuous time. T plus delta t will either be 0, and this happens with probability r delta t. So r is the resetting rate, and with the complementary probability 1 minus r dt, you just evolve it by just adding a random noise, white noise, with the d is the diffusion constant, and this is just a Brownian diffusion. Okay? So this is it. So r is the only parameter in this model. And this is the sort of model we introduced with Martin Evans 12 years back. No, it's 13 years back, 14 years back. And this is the sort of, the starting model, and it's very simple to analyze this model. And you ask, first thing you can ask, what happens in the long time limit? Now, there are many aspects of stochastic resetting. There's a mean first passage time to find the target that Supriya had discussed and John also discussed yesterday. But one of the principal things is that this is a very simple way to generate a non-equilibrium stationary state. Okay, and let's see how you generate such things. So how do you solve this problem? So it's very easy. So essentially, okay, you want to calculate what is pxt, probability distribution the particle arrives at x at time t, and given the resetting rate r. You start from the initial condition delta of x. So if there is no resetting, you all know that the distribution is just a simple Gaussian, e to the power minus x squared over 4 dt. And so now the question is, if I switch on the resetting rate r, what happens to this distribution pr of xt? Okay? So how do you calculate this? It's very simple. So you can write down a Fokker-Planck equation for this. So del p del t is, there's a diffusive term which is on the right hand side. So this is what you would get in normal diffusion. But now, because of resetting, if you are at x, with rate r you are going away from x, so this is a loss term. And there's a gain term, which is that if you happen to be at x, you can come from any other point by resetting there. And this is just the source term essentially at x. And so this is a partial differential equation. And you just have to solve this problem with the initial condition is this. And this is quite trivial. I mean, you can do by Fourier transform and whatever. But the solution, you can write it in a very simple way, which is quite suggestive. And this is the exact solution at all time t. So in this solution, there are two terms. So the first term is actually, the meaning of it is that, if you look at the trajectory, there's a possibility that you don't have any resetting between 0 to t. The probability for that is e to the power minus rt. And then it's a free propagation. So this is just p0 of xt, which is just a Gaussian propagator. Or you can have one or more resettings in that resetting object. And what you see is that in the long time limit, if t goes to infinity, this term drops out. And essentially, and this integral you can do it trivially. And this is just a exponential minus alpha naught mod x, where alpha naught is square root of. So this is the length scale. This is the amount of distance that the particle travels between two successive resettings. That's the natural length scale here, inverse length scale. And so this is the sort of simplest prediction. And you see that this is a non-equilibrium stationary state. So it is a non-Gaussian. It has a cusp at the origin, at the resetting point, and it decays exponentially on both sides. So even though it looks like as if it's a Gibbs distribution with an effective potential which is mod x, long, far away point to the origin by resetting, but there is no reverse move. So it manifestly violates Rittel balance. So there's a probability current flowing around in the configuration space. And therefore, this is a non-equilibrium stationary state. It's a very, very simple example of this. And so this was a prediction, and quite recently from the group of Yael Roikman, so they could measure this experimentally using a holographic optical tweezers, and you see that it matches between experiments and theory very well. Okay, so this is how, so today I'll just focus on the non-equilibrium aspect of it. So let me now go to the so there is another experiment which was done from the group of Siliberto in ENS Lyon, and this was actually again using optical trap setup, and this was discussed by Supriya yesterday. So essentially what you do is you let the particle diffuse for a random time, and then you switch on, this switching on an external potential. So if you take a harmonic potential, you switch on, so that confines the particle, so that mimics the resetting essentially. And during that time, you don't make any measurement. So, and if you make this potential steep enough, it's almost like resetting to the initial position at the center. And then you switch it off, the potential, and let the particle again diffuse freely for a random time, and then you switch on and switch off. So these two steps alternate. So this is how, the originally, it was also measured in this experiments in Siliberto. And so this question naturally motivated us then to ask, what happens if I, instead of one particle, if I have multiple particles here, okay? And so now you have, let's say, for a simple case, you just think of n non-interacting particles, okay? And you let them freely diffuse up to a exponentially distributed random time. Then you switch on the potential, let the particles equilibrate, and then you switch on and switch off and so on, okay? Just to alternate. So as I said, this is just mimics the instantaneous resetting to the origin. Okay? And of course, in real system, of course, you might have interactions, but as in these days, you can actually tune interaction by using all kinds of tricks in cold atom systems. So we decided to look at just this simple non-interacting particle. So the model is very, very simple. So in one-dimensional line, you have n particles. They are independent, n independent Brownian motions. They evolve, and then they are simultaneously reset to the origin by the trap, and after some random time with rate r. And you can ask, what is the joint distribution of the particles after some time t? And again, this is a non-equilibrium situation here because of violation of Dittel balance. So again, using this, very general renewal equation that I mentioned to you. So again, there will be no, exact solution of this at any time t. There is a term which is no resetting, so which is e to the power minus RT when there is no resetting up to time t. And then you have a free propagation, and because the particles are independent, so it's just a product of these individual Gaussian propagators. And then when there is one or more resettings, you look at the time since the last resetting event, and this is a free propagation again, and then you have to multiply by the distribution of tau, which is exponential, and then you have to integrate from 0 to t. Okay? So very, very simple. Okay? The particles are sort of, to start with, they are non-interacting, but what you see, okay, in the long time limit, again, this term will drop out, and you reach a non-equilibrium stationary state, which is given by this object. Now the interesting point here is that you see that this distribution obviously does not factorize. It factorizes inside the integral, but when you integrate over tau, they no longer factorize, which means there are non-trivial correlations between the particles, which is dynamically generated by this simultaneous resetting. See, the particles are going around, but when you simultaneously reset them from time to time, they somehow remember this, and this generates dynamically a correlation which persists all the way up to the stationary state, and you get a non-trivial non-equilibrium resetting gas where the joint distribution does not factorize. Okay? And so you can actually calculate the correlations. If you calculate just the normal 2-point correlation, it will be 0 by symmetry because of the Brownian propagation, x going to minus x symmetry, this is 0. So you have to go to the next order of correlation function, and next order of correlation function you can calculate exactly, and this is 4d square over r square. So this means it generates an attractive all-to-all interaction, and this is again dynamically because it's like all of us are free particles. You are allowed to roam around, but then there's a bell rings, and then all of you have to come back to one room, and that generates dynamically the interaction between the particles. Okay? Yeah, will you have a question?
One quick question.
Yeah.
If you did do resetting at a given time,
Yeah.
but you reset when it reaches the same position,
Yeah.
there
Yeah. You can also, in fact, with Arnav, we are doing some work on this recently. So you can generate all kinds of things. So all right. So this is it. And so the stationary joint distribution therefore has this very interesting form which we call the conditionally independent and identically distributed, which means that they are basically independent except for one parameter which itself is random, And they share this parameter. In this example, this tau, the time since the last resetting, is the parameter, which has an exponential distribution. But in general, it could be from any other distribution. So when you have a structure like that, the nice thing is that you see that inside the integral, inside the integral, inside the integral, this is the ideal gas structure. So you can calculate, as I showed you in the beginning, all the observables for this, and you just have to integrate over this guy. Okay, so that's it. So then you generate all kinds of non-trivial correlated structures, and I mean you can calculate all these observables exactly. Since there's not much time, I'll just flash the results basically. Okay, so explicit results. So the distribution of the gas is essentially, you can compute very easily. It has again this double exponential distribution. This is average density of the gas. You can calculate the order statistics. So the particles, their typical spacing between them is order 1 over n in the bulk, and near the edge is 1 over square root of log n. And okay, I'll not go into the details, but you can calculate the distribution function, and it's given by a non-trivial function, which is 2z e to the power minus z square, which is universal in the sense it does not matter whether you are probing the bulk or at the edge, unlike in the random matrix theory, and you can check with the simulations, it works perfectly fine. You can calculate the gap statistics. Again, it's an universal function. Universal in the sense it does not matter where you are probing. It's an inhomogeneous system. It's independent of where you are probing the gap. And it's actually given by a non-trivial function, which decays with a, sub-exponential decay e to the power minus z to the power 2/3. And you can calculate the full counting statistics, which is also given by a non-trivial scaling function. This is the number of particles inside an interval minus L to plus L. It's given by a non-trivial scaling function, which has a very interesting shape here. It sort of diverges at the edge when kappa is order 1, and you can calculate all the asymptotics and so on. So these are explicit results. Okay, so and then so what you have is that you have a whole class of solvable correlated gas by this CIID structure. Okay. And this is a sort of new application of stochastic resetting, and you can actually take ballistic motion, not just diffusive, Levy flights, and so on. And you can also use 2 different experimental protocols. So the first protocol is that you take a harmonic potential, and you just change the stiffness from with rate R1 and R2, just go back and forth between 2 stiffnesses. And again, this drives the system into correlatedness, and you can actually calculate, and it has exactly the same CIAD structure. And the second protocol is with Sanjeev, so we looked at the harmonic well, where you actually take the center and you just make a stochastic motion of the center. And that itself, because they all have the common center, that introduces correlations between these particles, which you can compute explicitly. And all of them have this structure of CIAD structure, which allows us to calculate everything explicitly. Okay? So let me summarize. So essentially, so what we have is, we have a whole family of solvable correlated gas with a non-equilibrium stationary state, and it has this sort of the mathematical structure which allows us to calculate everything explicitly. And there are various examples. I mean, this is the protocol I mentioned here. So Silibatu is now doing the experiments to measure our predictions, and so this, so it's very rare to find strongly correlated system, and that too out of equilibrium, for which you can calculate various observables, which are measurable experimentally. And this is what is done by this system. So let me just end with a sort of advertisement of our recent book with Gregory on statistics of extremes and records in random sequences. So some of the ideas that I discussed today, this is a very recent book which came out in the last July, and about the correlations and order statistics and so on, strongly correlated versus weakly correlated system. So these are discussed here if you are interested. Okay, thank you very much for your attention.
The correlations are mediated by that resetting time, right? The taus are, if for example, are xi and xj correlation.
Yes.
Happens through what? Is there a potential?
No, there's no. That's the whole point I was trying to say. It's created dynamically.
Right.
So imagine that again. In this room, we are all free particles. Okay,
right.
We are freely roaming around, but each of us are carrying a bell. Okay, and when the bell actually only one bell. So when it rings, all of us have to come back to this room. So if you keep doing this, even though between 2 resettings, you are totally independent. But the fact that you are actually coming back simultaneously at the same time, so that's the origin of correlations, okay?
Right.
And
So it's mediated by the resetting.
by the resetting,
By the-
essentially,
And,
exactly.
like they don't all come back to the same point, right?
Yes.
They all come back to their original points.
Yeah.
Xi comes back to xi0, xj
Right.
comes
No,
back
this
to
was for
xj0.
simplicity that we took the thing that we were all coming back to the origin.
Thank you.
Otherwise, you can do it for arbitrary initial positions also.
Thank you.
Yeah.
So the question was related to this Poissonian resetting. So if you are choosing some different scheme,
Yeah.
then your this
Yeah,
correlation.
the stationary state will be different, of course. I mean, but you can still, the CIID structure will still hold. I mean, actually, in many problems, what happens is that, I mean, it's hidden. I mean, in the sense that, the joint distribution is not always easy. In this particular example I discussed, it was evident, manifestly built in that e to the power minus r tau, the Poissonian resetting. But for example, in these other problems that I discussed, when you have a protocol where you have the two potential, you are just switching back and forth between mu1 and mu2, it's not obvious at all. You can solve the Fokker-Planck equation, but it's not obvious at all that it has a CIID structure. So you have to identify which is the parameter which has a common distribution, h of u. So that's not always easy. I mean, what I mean by this is so the point is that you can actually calculate this explicitly, but you have to have some integral representation like this. Only then you can actually calculate things. Otherwise, if you have a strongly correlated gas, to calculate anything is very difficult. The fact that it has an integral representation like this is not at all obvious. Okay. In fact, the general mathematical question is, if I give you a joint distribution, under what conditions can you write it as a CIID structure? Okay, that's not known in general. Okay.
Right, in general.
So,
Yeah, thanks.
yeah. Abulbu.
So the reason I asked you this question, I was thinking of a different problem, and these guys know it much. Your geographic vicinity knows this much better than me. There are these elastoplastic models,
Yes.
which is basically a stress diffusion.
Yes.
But as soon as the stress reaches an E
Absolutely.
stress, it's a resetting.
Exactly. So this is the, this is the,
And these equations have been written down, but there are no formal solutions.
No. I mean, at least in this context, you can actually. So there was a paper
what
by
I-
Sid Redner and Benjamin De Bruyn who actually first computed this. So their motivation was that if you look at the electrical network in Canada, for example, okay. So typically there's a blackout when it exceeds, the voltage exceeds certain threshold value. There's a blackout and everything gets reset. I mean, basically to zero. And then so this is what is called the first passage resetting. That means you have a level, and when you hit this level, you reset. So you don't reset randomly at random times, but you reset only
Yeah,
when
but
you
that's
hit some
saying-
level.
Right, so I think the people who do this amorphous plasticity
Yeah.
thing would benefit from using.
Yeah, no. In
this-
fact, people are already, people like Eric Bartha, they are already using this, for example,
Yeah.
okay, for the elastoplastic models, avalanche models, and so
Okay,
on.
okay.
So this is already done. So
Okay.
yeah, and one of the applications of resetting, basically, yeah.
Satya, this h of u in the previous case was the time distribution
Yes,
between resets.
right.
What is h of u here?
Here, so here is actually this is it's a little bit complicated. It's actually the residence time in one of the potentials. So I mean, like you have mu1 x square by 2 and mu2 x square by 2. So if you look at a trajectory, so it spends some time in this, some time in the other potential, some time in the other. Okay. So if you ask, what is the occupation time? If I look at a time t,
Yeah.
what fraction of time it spends in potential 1, for
Yeah,
example.
yeah.
So u is the fraction of time it spends in one of the potential.
Okay.
It's not easy to see that directly from this formula that it will be like this, but you can derive this essentially. Okay.
I see. Okay.
So that's what I'm saying. It's not always easy to identify what is the u variable. So sometimes you might be you have an explicit joint distribution. You don't know how to compute things. Okay, but could be that there is a hidden integral representation where you have this structure. That means inside the integral it's an ideal gas, and then you just have 1 or 2 parameters which are random. So then it's very easy because you just calculate for the ideal gas.
Yeah.
So you have an explicit formula for these things, and then you just integrate over these parameters. Okay. So that's the mechanism of this CIID structure.
And these potentials switch instantaneously.
This
They-
potential?
I
Sorry?
mean, they switch instantaneously. There is a.
Yeah, there's a R1, R2, but you can actually ask
No, I
also-
mean, they don't take at once you decide to switch, you know.
Yeah, you switch it instantaneously, yes. You can ask this question that, if you do it slowly or something with the time dependent, then what happens? I mean, all this, that's what I was telling you yesterday. The stationary states are actually very sensitive to these kind of things. I mean, it's not, yeah.
Thank you.
Okay, let's thank Satya once more.
You can present it.
Okay, great. Thank you.
Hi, can you hear me? Thanks Arno Pinaki for inviting me. It's a great pleasure to be here. This is my first time at IMSC Chennai. The campus looks beautiful, very quaint. Great to be here. Just very briefly, I'm at the Center for Nanoscience and Engineering at IISc Bangalore and also associated with the Department of Physics. I also have involved in a startup that we had co-founded, and I'm going to tell a little bit about how self-propelled magnetic nanomotors have resulted in a medical device startup. Also, I realized from the audience that it's very diverse, and in our group, we sort of have two vertical threads. I'm not going to talk about our experiments on quantum fluids, where the question we are trying to address is, how does a two-dimensional solid melt at 0 temperatures? But rather, I'm going to talk entirely on nanomotors or nanoswimmers. And these are the sort of questions that we are addressing. How do you make a model active matter? And how that can lead to some form of a new therapeutic strategy for medicine. Before we start, let me acknowledge the large number of collaborators from multiple different disciplines who have contributed to this work. And definitely a large number of students, very talented students and postdocs who have done this work over the years. To tell you the basic premise of our experimental system, we are talking about a wet active matter. We are talking about a colloidal particle, a very small particle moving in a fluid. The Reynolds number is significantly less than 1. So in other words, the motion is entirely dominated by friction. This is, of course, the world in which microorganisms swim. And just to remind you of Purcell's paper, the typical motion that is used are either the corkscrew motion of an E. coli bacterium or the way a spermatozoa swims, which is a long, flexible filament that beats and moves forward. Of course, this is not the only way to move at low Reynolds numbers. One can also imagine some form of a phoretic strategy in which you have an asymmetric structure, and through either chemical reactions or light or electric field, there is some form of a gradient of some molecules to the left and right of it, and as a result there is a phoretic velocity that one would achieve. I'm going to focus entirely onto this line of work, just to tell you a little bit about the type of applications that people imagine would happen here. It's of course all started with Richard Feynman's very famous lecture called Plenty of Room at the Bottom, and there he talks about how these things, little machines, he calls it miniaturized surgeons that can be put inside human blood vessels and going and delivering drugs and treating diseases and things like that. If you were to make a research program out of it, the type of questions that you want to address is, firstly, how do you move very small objects in fluids and gels? You of course want to do it with good control from a distance, and you want to really fabricate and maneuver a swarm. You want to give it multiple functions so that they can do the sort of things he talks about. Interestingly, because we have a swarm, there can be interesting collective behavior, and that can of course result in some form of intelligence or tasks that single swimmers or single motors cannot do. And the type of applications can really be, there is no limit there. Now, one first question that one needs to address is, how do you power these motors in order to make them move in fluidic environments? And in this respect, magnetic manipulation is extremely well suited because it's fuel free, it's very, very biocompatible. It can, because it's remote, it can work deep inside an organ. And I want to maybe stress upon this point a little bit and also tell you what I do not mean by magnetic manipulation. So this is not a magnetic nanomotor in the sense I want to use it. So here you have a little Eppendorf tube with some magnetic particles. If you hold a magnet nearby, of course all the particles are going to go near the magnet. Now, if you want to look into it a little closely, this happens because there is a strong gradient field, and this particular strategy will not work once you take the magnet a little bit far away, or if you make the particle size smaller. It's just the way the force depends on the magnetic field. So one of the main motivations or constraints here is that you want to use some form of a homogeneous magnetic field. There is a very nice paper from the UTH Zurich group about how should such systems work. The strategy that we have adopted in our group is to mimic the motion of a corkscrew, and what we have basically is a artificial screw with a shown in green here. The red is the magnetic moment. In the presence of a rotating magnetic field shown in blue, the screw rotates and therefore translates. And this is really sort of the version 0 of our experimental system. But I'm going to build upon this a little bit. The head here is just something that comes due to our fabrication once in a while. We can avoid it. It's not a necessary aspect of this experimental system. So therefore, there are certain differences between this and a typical E. coli that is swimming. There is no counter-rotating head. There is no flexibility in the filaments, so on and so forth. So we are talking about rigid corkscrews sort of going through, propelling through a liquid. That's what we are talking about. The experimental system, let me tell you how we make these tiny corkscrews. This is made using a technique called glancing angle deposition. The idea is you have a substrate at a very extreme angle with respect to some material that you are evaporating, that you are melting. And this angle alpha is of the order of 85 to 86 degrees or so. At this extreme angle, the material that comes will go and stick to the substrate, but then any material that comes subsequently will get shadowed because of the part that has already been evaporated. So what you use here is to utilize this shadowing to make structures of different shapes and sizes. So if you do not do anything, there is just going to be some columns that are going to get grown on this substrate. But then if you start rotating this substrate, you can actually control the direction in which the columns grow, and simply by controlling the rate of rotation and the evaporation rate, you can make structures of different shapes and symmetries. So this is, for example, a helix that's grown, and well, this is very often what we have made in the lab. And just to stress upon the versatility of the technique, you are actually talking about a wafer scale system of small helices. So we are making 1 billion helices in one go, and as opposed to many other experimental techniques which are somewhat more limited in yield. So this really allows you to go and deep into sort of looking at collective properties and stuff like that. So just to also stress upon the versatility or the the range of parameters that one can get in the experiments. We are talking about swimmers. This is one of the largest, a couple of microns long, almost a micron width. And in opposed to this particular swimmer is one of the smallest in the lab, and here the scale bar is 500 nanometers. So we are really talking about more than an order of magnitude in what you can achieve in your experiments. Typically, these objects are made of silicon dioxide, which is just very easy to grow, and then we include some material, iron for example, into it, and all these experiments are done in multiple coils of our lab depending on what type of applications we are talking about. So it's a triaxial Helmholtz coil, which means you can produce time-varying magnetic fields in any direction, any polarization, and also observe it simultaneously in microscope. This guy is a little bit bigger because we also put some animals out here for some of our biomedical experiments. But then very often we are able to see this with a really reasonably good precision. The type of motion one can achieve is definitely beats Brownian motion. Simply by changing the sense of rotation of the field, you can make the swimmers go north and south, or if you want to do east and west. And if you want to get some publicity, you can try to write some G-clef sign, some music sign. And of course, you're not just limited with one swimmer, but you can actually have a swarm of swimmers all actuated in a nice manner. Sure. Absolutely. Thank you. Thanks for, I missed mentioning this. These experiments were done with a typical Hilescher geometry. So we are talking about anywhere between 10 to 100 microns. But we can also do it in bulk fluids. It's just you have to stabilize the currents very carefully. That's all. Sorry, I had a little difficulty here. There is. So we actually set the direction in which they should move. So it's entirely set by the plane in which it's always normal to the plane of rotation of the field, and the direction in which it goes is set by the helicity or the handedness of the helix. Okay. So it's basically. So effectively, it's the direction of motion is always perpendicular to the plane in which the field rotates.
But the orientation
No, the orientation is set by the plane. So you can, and I'm going to come to this in just a little bit. That's what the trick is. Okay. So yeah, so that means if you have lots of them, they are all going in the same direction, and that's something that's important. Yeah, but we will break that. Right, I'll go a little bit, so I wanted to mention, yeah, so you have a swarm, and then starting from this paper about 15 years ago, there has been actually multiple tech transfers on this, and there are people who are trying to put this in brain, in teeth, and a couple of different places. So in fact, there are some clinical trials that are happening right now with this particular technology. Initially, I think starting from our first work, one of the main motivation was to see how these things move in different biological fluids. And in fact, over the years, it's kind of funny, we sort of starting with water. Of course, there is teeth. You're actually observing this motion in live, in human teeth. You can also move these things inside living cells. In blood, this is not in vivo, but ex vivo. This is outside, taken outside. This is a great tool to study biophysics of cancer. This is motion in cancer extracellular matrices, and this is something new in which you're barely seeing it, but we can now observe the motion of a swarm of such swimmers inside live animals taken with in vivo imaging. So we are actually very close to the fantastic voyage dream in some sense. So this is the peritoneal cavity, which is sort of a fluid-filled cavity in the gut. And is connected to many organs. The experimental system, you can have multiple materials and functions, so which really allows you to put in lots of different functionalities in one go. And so, for example, here the iron is placed in three different islands. I'll go a little bit quickly because I saw some optics related talks. You can actually integrate silver nanoparticles onto the swimmers. So now what you have is you can have plasmonics integrated with magnetic swimming, and one of the aspects of plasmonics is when you shine light, it has a very strong light matter interaction, so it works as little optical traps. So this is a fun experiment that we did some time back, in which we took the swimmers, they have these plasmonic properties, you shine light next to some colloidal particle, so of course it works like a little trap, and then you can of course take it from point A to point B, turn the light off. So what you can now do is to sort of have trap, transport, release little colloidal particles with very, very low light intensity. And the light intensities that are used here are orders of magnitude smaller compared to a standard optical tweezer. So that's the sort of things we need to you can use, you can combine it with other fabrication schemes. I have been extremely lucky to be located at the Nano Center at IISc, where all these facilities are available, so which really makes life very, very easy. And of course, you can also do standard chemistry in which you can functionalize things to this helical swimmer and give it new types of properties. I'll go right into the business. So over the years, you could imagine that we have studied this motion in reasonably good detail. There are some caveats that we must mention. So of course this is the propelling motion that I keep talking about, but if you think about it, you see this particular motion is equally possible, right? You can have either a propelling as well as tumbling motion in both the cases. The magnetic moment rotates in sync with the external field. So of course the question is what happens, and one can actually write down and one can observe this type of tumbling motion as well as this type of propelling motion and motions in between. So these sort of things can be studied, can be calculated. Yes.
Can't you stop the tumbling? Can't you stop the tumbling by using another constant field?
Right. So then it becomes some form of a precisional magnetic field effectively, and you can also calculate the dynamics under such precisional fields. Right, so typically what happens is when it tumbles, it actually is again very close to the surface, so it sort of walks through, sort of a thing. I guess the key point is, there are lots of interesting, one can look into the details of this type of dynamics, look at the, the geometry, the surface effects, the magnetization strength, so on and so forth. I want to highlight, and I'm not going to talk about this, that this is really a great system to also make local rheological measurements, and I have some work, we can discuss it some other time, where we can actually make little rheometers for even to make rheological properties of inside living cells. Okay, so that's the type of things that has been done and in process. The focus of this talk is, I said all these things because, I wanted to sort of describe the experimental system in some detail, and I'm going to basically start from that question that was asked, that, if you have helical swimmers, and if you have a rotating magnetic field, all of them move in the same direction. And this is, of course, not the property of a self-propelled system of swimmers, right? They're not self-propelled, they're just driven. And why do we want to do that? Well, of course, what we have is, I would call it still a propeller, which is externally powered, but more importantly, the direction of motion is determined experimentally, and this will be a zero force but a non-zero torque system if we use the typical language that is being used. On the other hand, if you take standard biological swimmers or even some of these catalytically powered nanoparticles, you will see that, well, the source of energy could be chemical or external, that doesn't matter, but crucially, it's a zero force, zero torque system in which the direction of motion is not governed experimentally, but only governed by either orientational diffusion or governed by interactions. So the question that we wanted to address is, well, can we make an all magnetic active matter where the fuel will come from small magnetic fields, as we have been doing in our experiments. However, we do not specify which direction they should go. So their direction should only be governed by interactions with each other and the surrounding, similar to the chemical motors. That's the problem that we wanted to solve. And the motivation of this is, of course, to see what happens to such swarms. And we have just started to do this now. But let me tell you how one can have an all-magnetic, a self-propelled particle in which the fuel is small magnetic field and the direction is not given. And the answer is extremely simple. All that you have to do is you have to, this is the helix, and then of course if you have a rotating field, they're just going to go in one direction. But imagine instead of a rotating field, you give a simple oscillating field, and in other words, you only have Bz, which is perpendicular to the plane at which the object is residing, and then the moment is going to point upward, and we are just looking at it from the end of the helix. And then when you go to plus z to minus z, the helix would have to turn, right? The magnetic moment would have to point downward, and when it does that, it can, the helix can go through either a clockwise turn or a counterclockwise turn. So you can do a clockwise, or you can rotate in the counterclockwise turn, and because the helix is a chiral object, the clockwise turn can result in maybe a forward motion, the counterclockwise turn will result in a backward motion. So whenever you go from a plus Bz to minus Bz, is going to have a little bit of a motion. And when you go it back, when you again get the field up, so you're just oscillating the field, again there will be either a clockwise or a counterclockwise motion to go back up. Now, the key point here is, at no point of time are you telling the helix which way it should orient. Okay, that's the key point. And that's what you are seeing in this movie. So these things, when you do the experiment, you find out that, well, there is not an equal probability to go from, to whether it should do clockwise or counterclockwise, when it goes from this state to the plus Bz to the minus Bz state. And then similarly, there is a specific way in which it goes from the minus Bz to the plus Bz configuration. And this simply happens because there is some natural weight asymmetry in the system which makes it always turn in one way, and therefore it goes forward. And then when you turn the field back towards plus Z, it comes back using a backward motion. So really what we did, and this is V1, is some kind of a magnetic reciprocal swimmer, if you use Purcell's language. Yes, Mahesh? And that's exactly what we are doing here. It is what we have is a scallop. Yes, I will avoid it. Just one more slide. So what we have is a reciprocal swimmer. And this reciprocal swimmer is simply going back and forth, but we do observe an enhanced diffusion even for a reciprocal swimmer, and this is actually, so this is Brownian motion without doing any magnetic field, and now it's just going back and forth. It shows some form of enhanced diffusivity, and this is not very surprising because as it goes back and forth, it's also doing some form of an orientational diffusion in its plane. So in other words, when it goes, it can diffuse and then it can come back a little bit. So effectively what you have is a rotational diffusion. So what we have is, it is an active matter, it's still boring, it's still a reciprocal swimmer, right? So that's what we have here. So of course the next question that one should ask is, well, can you make it, can you break the reciprocal symmetry? And just to give a little bit of details of how this whole thing is working, you do have the plus Bz here, this is your magnetic moment, this is a little bit of a weight asymmetry, which says that when you go from plus Bz to minus Bz, it should take a clockwise turn to go back, right? And then when you go back up, it should go back by a counterclockwise turn. The trick is really very, very simple. All that you should do is when you make it go from minus Bz to plus Bz, you should just, and when you do this, well, about 100% of the times it's just going to do a clockwise turn and therefore go forward. The trick here is you just need to go a little bit faster when you go from the minus Bz to the plus Bz term. And when you do that, it's basically, and you can show it with all the math, we did it in our papers, that there is going to be an equal probability to take either the counterclockwise or the clockwise paths to make it point towards plus Bz. So effectively what you have is it's not really nothing but a ratchet that is being used. And this, of course, only works in the presence of thermal fluctuations. The key point is, after one such cycle, you have some preference towards clockwise turns, at least in the picture that we have shown here. So, of course, if there is no thermal fluctuations, this is simply going to be back and forth. So, the noise is indeed necessary to break this counterclockwise-clockwise symmetry. So, what we are really using is the Brownian ratchet to move things forward. These are some experimental results. So, you know, if you can do slow and fast switching, you can actually go from, when the slow switching is perfectly deterministic, there is this fast switching which gives some range of stochasticity. And the interesting thing is, you can actually compare simply by varying this ratio of the times that we use in the experiments. You can actually go from a fully reciprocal to a non-reciprocal swimmer. So you can actually control the degree with which you are able to control this. This was the work. So, and really what effectively we are doing some form of a ratchet out here. Okay? So that's the way in which you can make it go from driven to a self-propelled swimmer. And the next that we want to address is, what are the differences? If you take a swarm of such swimmers, what are the differences? We have a driven versus a self-propelled system. In order to do that, I'll start from here. Well, maybe this is the time when one should ask, well, how do the swimmers interact with each other? At very short distances, they of course interact magnetically, but at the typical distances that we have in the experiments, hydrodynamics is far stronger and far more long-ranged. So one of the things that we did is to actually look at the hydrodynamic flow that the helix produces as it swims. So this is a work in collaboration with Alex from Technion, and what we did was we took the swimmers and we did not consider the swimming in bulk medium, but we did assume things to be reasonably close to a surface. And I don't have a pretty picture, but effectively what happens is when the swimmer swims and it creates this rotlets, because of the presence of the surface down there, effectively what you have is a very strong lateral flow. So this is an interesting swimmer in which if the swimmer is going from left to right, most of the flow is actually going from north to south. It sort of drags things, and my right hand is actually pulling the left towards it. So there is some form of a non-reciprocal hydrodynamic interaction between the swimmers, which actually results in which is kind of interesting when we go to the active case. So back to the driven system, where we simply have a rotating field. I'll first show you the boring results. So this is of course when a lot of these things are all going in the same direction and they are really not interacting with each other because, well, it's a low frequency, low density, they are moving very slowly. Things become interesting, a little bit more interesting, when you have a large number of swimmers that are actually, we wanted to drive it from left to right, but what you would see is a very strong drift towards the right, and that's really because they are all sort of, as they try to go in some direction, they're also making them drift in a sideways because of the hydrodynamic flow. And the interesting thing about this is, and this is the part that I like, if you really analyze it very, very carefully, you would see that the sideways drift depends strongly on density. So now what you have is an interesting handle with which you can actually have swarm control, and you can look at the response of the swarm and connect it towards the local density, and that actually is could lead to interesting ways in which you can control the swarm. We are just in the process of finishing this. Things get far more interesting when, instead of a rotating field where everything is driven, when you start looking at how things happen in oscillating fields when everything is active. And in this particular case, I mean, of course, this is really some form of a strong, dense collection of active particles. We have taken a few particles and plotted their trajectory, and of course we start seeing this type of swirling motions, and this is sort of prototypical active matter, wet active matter with strong hydrodynamic interactions. We do not see MIPS or any phenomena like this. We are just starting to look into this very, very carefully. Sriram is trying to build some form of a field theoretical model out of this. So there is a lot of work in progress. There are some funny things we observe, and I'm just going to show you this. Well, firstly, for no reason, this particular little defect, some big some stuff that's not even magnetic started moving in one direction. Can you see this very closely? And if you can observe the dots here, and this is kind of interesting, you will see that they will all come together, they are accumulated, and then suddenly they are all going to go all at the same time. So, I mean, you have to look at this part. We really tried to make the movie nicer, but I can maybe show it to you later. So they are all here, all here, all here, all here, and boom, now they all go away together. We don't understand what's happening, and this is really the reason why we need some serious theory to understand this better. But a lot of effort went into building this experimental system, and just to give you an idea, I mean, of course, this is just some toy model, and these are just some of the little hydrodynamics toy model sort of stuff we did in the lab. Again, we don't understand this very well, but it does seem like some strange behavior. I'm going to just say that, well, the typical diffusion constants that you can get out of these active particles is almost, more than 50 micrometers square per second. Just to put things in perspective, this is almost 300 times compared to what is there in the passive case. So they are really very, very strongly active, very high Peclet number, and I'm just going to say that this is work in progress. Okay, so hopefully we'll be able to report you something better in some time. I have another. Sorry? Okay. Thanks. How does this result in a new therapeutic strategy? And this is a question one can ask for everybody. One of the possible ways in which active matter can be used for new type of therapeutics. So one of the key points to note here is, well, because the mean square displacement is higher, self-propelled objects can move in all directions, they can go in different ways, and they can cover more areas in less time. And that's one of the benefits of having active matter. And one of the places where this really becomes very, very useful is actually the inside of the tooth. So I don't know how many of you had root canal procedures out here, but let me remind you a little bit. In root canal, this is the structure of the tooth, the part in white, and what you have here is the pulp. And typically in a root canal, the dentist comes, takes the pulp out, and they put some gutta perca or some sort of a thing to just seal it off for good. So the tooth is not alive or not viable anymore. So the pulp is really where the bacterial infection happens. That's where the decay happens. But if I were to go a little bit into the structure of the tooth, this is the so-called dentin tissue. The structure of dentin, here this is the pulp, this is the tooth. Dentin, this tissue, is made of a large number of tiny canals. And these canals are about a micron or so long in diameter and about a millimeter or so in length. So if I were to sort of say it in a very simple term, what we have is a cylinder. You can imagine the tooth being concentric cylinders, and they're being joined by little canals that are going radially outward. Now, one of the biggest problems why 10% of root canals fail is because of the bacteria that are sitting out here, which the doctor is not able to remove during your root canal. Typically what they do is they put sodium hypochlorite, which is bleach, and they hope that the bleach is going to diffuse through the dentinal tubules, go all the way up to a millimeter and kill the bacteria. And because it's bleach, this typically doesn't happen because the time it takes for the green one, this is typically the diffusion constant of bleach, is probably going to be, it's to go all the way up to a millimeter or so will take many, many hours. So of course this is one place where active particles are very useful, where you can go in all directions and cover a lot of region, go all the way up to a millimeter very easily, and something like 8 microns a second is actually quite good, because you are able to go to the depth of the tooth within about a couple of minutes or so. There are lots of companies and lots of technologies who are actually trying to solve this particular problem, because 10% of the number of root canals, just imagine, we all have, well, 28 teeth, and just if you do the numbers, it's just it's really staggering. But none of them are able to, none of these other techniques are able to go deep. So of course this is what we did. We put the swimmers, and what you are seeing here in this movie is actually motion through the dentinal tubules. we can actually drive them because these things are really, really tiny. And this is one part where driven versus self-propelled makes a huge difference. For the self-propelled ones, after some 20 minutes or so, you can go only to, in one of the directions. So this is the central pulp region, and this is the dentinal tissues. Of course, you did not move much over a certain time. On the other hand, with self-propelled, we could actually cover the entire region in a much shorter amount of time. Just to tell you a little bit of application, so you can actually make them actively diffuse in all direction, cover all of the tooth, and then you can use a rotating field and even retrieve them one after another. So that's again one of the benefits of having a system that can be both active and driven at the same time, simply by turning a magnetic field knob. In this picture, what you are seeing is here these are swimmers, the green points. Here you are looking at the green points correspond to living bacteria and the red points correspond to dead bacteria. May not be very useful here, but the key point is you can take the swimmers and actually kill the bacteria in the location that you would want. I'm going to end my talk here and just say that, well, you can compare the key difference between some form of active propulsion versus some form of a rotating field, and you would be able to actually see a dramatic improvement when you have self-propelled objects moving in all directions. And this is again partially the reason, because here topography is making a huge difference. So what we have here is things from the central region of the pulp are going in all through the tubules in all possible direction. You are not allowing them to reorient. So effectively, if you think about the active Brownian particle model, you are not allowing them to reorient. So as a result, the overall displacement that you can achieve in a certain amount of time is significantly more because of the topography. So active particles under confinement with reduced orientation can really play a very important role in covering a large region in a small amount of time. With that, I would like to conclude. The key point that I spoke about today is you can make the swimmers multifunctional, and this is it's work in progress of how we are studying making this as a model system to study active matter, and there is some relevance to practical medical applications. The part that I did not tell you about today is this is also a fantastic new tool for intra and extracellular mechanical measurements. With that, I would like to thank you for your attention.
So you said that the reciprocal sweepers are kind of boring, but if you put many of them together, the many body effects are not boring. They would not drift, the reciprocal swimmers, but if you have two of them, they'll still rotate. The air will rotate. If you have a strongly confined geometry and you have a reciprocal, quote-unquote, pneumatic swimmer, a pair of them can rotate. A single one cannot.
Yeah. Indeed, there are these interesting fun papers from I think Eric Logger about no many scallop theorem sort of a thing. So you can have two reciprocal swimmers. If you have the right phase differences, they will behave like a non-reciprocal system. So.
Yes, but more importantly, the many body effects can give you a sort of a state which is aligned but spontaneously rotating.
Okay.
Things of that sort can happen.
Yeah, so I don't know if that will happen if you confine it in 2D.
Yeah, this is when it's confined.
Oh, is that so? Okay.
This is, yeah, I mean, it cannot happen in 3D.
Okay.
It can happen in a 2D interface, or it can happen in
But you are talking about which type of rotation? You are talking about
this. So this is the long axis.
Right.
Rotation. So if you have two of these objects.
Okay. Yes. Absolutely.
This is a subjective query, so there's another school of thought which claims that the Janus particles are also extremely helpful in drug delivery and stuff like that, because of the targeted motion and self-propulsion. Do you would like to compare what the pros and the cons between the two strategies?
Well, I suppose one of the benefits of Janus particles is you can probably build in chemotaxis and rheotaxis, probably chemotaxis very easily. And there is this interesting work from the Barcelona group who's using this swimmers to, I think, target some cancer of the urinary bladder.
Sergei's group. Yeah.
Right. So Samuel's group is doing this, and what he has done is he uses urea as the fuel, and then he's able to actually penetrate deep inside the cancerous tumor. And here again, I think chemotaxis is one place where the Janus motors make a very strong case. So.
I have a question about this retrieving this swimmers using this rotating field, right? When you retrieve from this dental this thing. So when you put this rotating field, if it retrieves from one side, doesn't it push the other swimmers this thing? So how do you retrieve everything together?
Yeah, so you have to create a flow, and over a time you effectively can collect. Sure, so some of them will indeed go in the other direction, you're absolutely right. But the whole thing is, you can imagine there is a wall and there are a few holes, so most of them are just going and banging their head against the wall. So. No, so this comes from the natural topography of the dentinal tubules, but we have also checked it in other types of sort of gels. So in gel-like media, you would actually see that the reorientation time is significantly longer. So as a result, it sort of moves effectively, it follows T-square rather than T dependence for a longer time.
Okay, so it sees the boundary and then it doesn't.
It does not orient. So it just, if there are two of them, you know, they will continue going in this manner for a longer time. And this actually is very dramatic. These are orders of magnitude improvement.
I had another question. So maybe I just didn't follow. You had an expression for the MST?
I think it's incorrect.
So
Yeah, I think I missed a term. I just noticed it a little bit ago. There is some problem with that expression.
Which is the.
No,
the
I think
V0 is.
V0 is the active velocity, but I think I missed a term
Which
there.
is emanating from the magnetic field.
Yes. How do I go there? Oh, so V0 is the active velocity, which is the effective active velocity that you would get. I'll just go quickly there. Sorry, 1 second. Yeah. So I think.
Which you will calculate from the.
That's the self-propulsion velocity. So we just did the fitting of this mean square displacement, and this is in turn a function of the fast and slow time scales that we put in the experiment. So you can control that. And tau r is just the rotational diffusivity of the swimmer.
Thank you.
I have few questions related to the experiments. So, what happens near the boundary when this particle goes to the boundary?
So they are already close to the wall, and if they are, and if the interaction is too strong, which depends on sort of the chemical properties, they will not only go forward but also have a strong sideways motion, even in isolation, even a single swimmer. Typically, we make them charge so that they are somewhat farther away from the surface, so they move in one direction.
So they don't follow the boundary when they reach near the boundary?
So they would have a sideways motion if they are very close to the boundary. And I'm talking about the one that matters the most is if the swimmer is going in this direction, how far is it from the bottom surface? Typically.
And that PIV that you showed, so yes. So
good experimental challenge. It depends on the viscosity. We typically stay between 200 to 500 nanometer particles. It depends on the viscosity.
And won't this tracer particle change the dynamics?
Yeah, so we don't think so because the densities are very low. This is really averaged over a very, very long time.
One last question.
Thanks.
Right. Yeah. Yes. So we are still. You can calculate the rotational Reynolds number. It's still 10 to the power minus 3 or so.
Okay. Let's thank Ambrish for his nice
Thank
talk. So we'll meet at 11:20. Back here.
Session right